Consider this language: a power I, b power j, c power k, where j is strictly more than I plus k. Now we are asked to construct CFG for this. What we will do, we will try splitting this into some known CFGs. So we usually substitute and simplify, so we try that approach. And this. Okay. But I should ensure j is strictly more than this. Okay. So what I do, I need to introduce one more so that the excess part is taken care of. Okay. So what am I saying? You say j equals I plus k plus some m, and that m is at least 1. Correct? There will be some excess b's that will be captured over here. That's all we are saying. So a power I, b power, this is strictly more, right? So what? So we write this as this followed by b power m times c power k. This we further simplify and say a power I, b power I, b power k, b power m, c power k, a power I, b power I, this you rewrite b power k, c power k. Remember, m is at least 1. Now, this we know, and this also we know. So, meaning this L, you can see it as L1, L2, L3, and L1 is a power I, b power I. Let's assume I is greater than or equal to 0. L2 is b power m is at least 1. And L3 is b power k, c power k, k is at least 0. Fine. Now, we know how to write for L1, L2, L3. So, L1 says A implies small a, capital A, small b. I is at least 0, which means epsilon is allowed. L2 says B implies small b, capital B. M is at least 1, so which means B. And L3 says capital C implies small b, capital C, small c. And C can be epsilon, so we allow this. Fine. Hope are you all with me? This gives you a power I, b power I, and this gives me b power k, c power k, and this gives me b power m. Now what is L? L is precisely concatenation of L1, L2, L3. So now to get L, you say S implies A, B, C, and A implies whatever we have written above, and B implies BB, C implies B, capital C, small c, epsilon. This gives you a larger message if L1, L2, L3, for all of them we have context free grammar, then the concatenation, which is L1 concatenated with L2 concatenated with L3, even this as a context free grammar. Equivalently, if you have push down automaton for L1 and L2, their concatenation also as a push down automaton. Fine. So just like union, concatenation is also closed, meaning take two languages which are context free and you concatenate them, and the resultant is also a context free grammar. Or for the resultant language, one can obtain a context free grammar using L1 and L2. Okay, it's quite interesting, but the fundamental message is the following: do not just look at this and then try building CFG, and try simplifying, bring it to a form which is known to us. Then you see whether it is concatenation operation or union or intersection, CleeneStar. Choose the appropriate operator and then take CFG or PDF or the sub ones, combine them to get the actual one. Fine. So on the similar line, let's explore CleeneStar. Consider this regular expression, say 0, 1 star or 1, 1 plus 0 star. So set of all strings generated by this language, they satisfy this pattern. Either they come from this pattern or they come from this pattern. Now we know that a finite automaton exists for this, which means you can construct an equivalent regular grammar. And every regular grammar is also CFG, so therefore you can easily conclude CFG exists for this. So from this regular expression, we get NFA with epsilon, and subsequently you can convert that into a DFA, and you can get regular grammar from this or regular grammar from this, and all regular grammars are also CFG. Okay, so straightforward. So this clearly tells you that you are CleeneStar, then you can obtain CFG, provided you get to see that it is regular, and of course it's a regular expression, so which means it must be regular and accepted by some finite automaton. But there is one easier way out. One can construct just by looking at this. Now S implies A or B. Using this non-terminal, we generate this. What is that we want? We want this 0, 1 repeatedly. So 0, 1, introduce this non-terminal. So which means 0, 1, 0, 1, A, again 0, 1, 0, 1, 0, 1, A, 0, 1, 0, 1, 0, 1, A, and so on. Epsilon is allowed, so introduce epsilon. Or look at B. B says there are two things, and one can do CleeneStar on that. Correct? So what it says is you do CleeneStar on this or this. Okay. So now using this, how do we generate this part? So we have to say 1, 1 plus 0 times B or this. So this clearly tells you that 1, 1 plus 0 followed by B, and this you can repeat any number of times. And for this B again substitute, 1, 1 plus 0 B, again 1, 1 plus 0 B, and so on. So now this clearly tells you that S implies A or B, and A implies this CleeneStar, and B implies this CleeneStar. 1, 1 plus 0 B followed by epsilon. Fine. In case you want to simplify this further, yes, this can be done. So I can say S implies AB and A implies 0, 1 A or epsilon, and B implies, I say, capital C followed by this followed by epsilon. Now with this we keep getting CB, CB, CB and so on. And what is the value of C? C can take either 1, 1 or 0. So this can be further simplified just by introducing one more non-terminal, we get this. Fine. So this tells you that the operator KleeneStar is closed with respect to CFG. So what is this telling you? If L is having a context-free grammar, implies that L star is also having a context-free grammar. Fine. We know that this one is regular, therefore CFG. This one is regular, therefore CFG, which means the star of this is also having CFG. And we in fact combine two things, L1 star union L2 star. Fine. Good. What about the intersection operator? So think about if L1, L2, if both are having CFG, can we construct CFG for L1 intersection L2? So I'll give you an example, just explore how things work. So let me take A power n and say B power m and followed by say C power k. Now if all are something like no condition at all, n is at least 1 and m is at least 1 and k is at least 1, then you can construct L1, concatenate with L2, concatenate with L3. So you can write this as L1, L2, L3. Supposing these two are same, say A power n, B power n, and this is same as this, followed by C power k, then you can write this as L1 and this as L2. Now what about the case where all three are same, A power n, B power n, C power n? Now can we construct CFG for this? Okay, so this is one question. Now one can bring other conditions also between n and m or among n, m, k, some condition. But to start with, the simplest one is this, is A power n, B power n, C power n context free. Okay, so think about this. Then we will look at other related questions which will have some flavor of this. For example, let me say A power n, B power n and C power k. L2 is A power n, B power m, C power m. Okay. Maybe some other symbol, A power p, B power m, C power m. Now this one as CFG, this one also as CFG. Now what about L1 intersection L2? First, you identify what all strings go into L1 intersection L2 and whether L1 intersection L2 and this language are they related. Supposing you show that CFG exists or you prove that CFG does not exist, then that will help in answering this question. So spend time, understand this and understand these two, followed by L1 intersection L2. We shall revisit and explore more about this.